Hello, hello, hello. This is Nicholas, and I have covered in the previous two videos. I did a video on second-order linear homogeneous differential equation of constant coefficients, where the characteristic equation, in other words, b squared minus 4ac, is greater than 0. Where in other words, where there's two distinct real roots. Did the case where b squared minus 4ac is equal to 0, where we have one root with multiplicity 2. Now the only thing that's left is where b squared minus 4ac is less than 0. In other words, complex roots. And this is probably the most interesting case. So remember, so let's say we take the characteristic equation. We take ar, let's I don't want to use this. So let's say it's instead alpha r squared plus beta r plus gamma is equal to 0, and we solve this characteristic equation, and we get that r is equal to a plus bi. This is why I use the Greek letters here, alpha, beta, gamma, because I didn't want to use ar squared plus br plus c, because I was going to use a and b here. I didn't do it just to make it more complicated. So r is equal to a plus or minus bi. Let's say we get that as a root. Then what we can say is that a particular solution, at least, would be equal to e to the, and let's just do the positive version for now, e to the a plus bi t. Now, let's look at this e to the a plus bi t. We can do some more stuff with it. So let's make it e to the at times e to the bti. Now, I hope you remember, and I've done a video proving this without calculus, and I've done a video proving it with calculus, that e to the I theta is cosine of theta plus I times the sine of theta. So here, theta is just bt. So this is e to the at times the cosine of bt plus I times the sine of bt. And now we can make this e to the at times the cosine of bt plus e to the at. All right, because I'm going to add something else in later. Let me do a little space. I e to the at times the sine of bt. And now, technically, the most general solution, y, would be a linear combination of these two building blocks. So in other words, y would be equal to c sub 1 e to the at plus c sub 2 I e to the at times the sine of bt. And this is, in fact, the most general solution. Sometimes you'll see it written as y equals just c sub 1 e to the at cosine, I forgot the bt, cosine of bt plus, and they'll just write it as c sub 2 e to the at times the sine of bt. Personally, I like to keep the I, because yes, if I were to give you an initial value and you were to solve for c sub 1 and c sub 2, I would have to actually give you two initial values. I would give you, say, like y sub 0 is equal to 1 and y of 0 is equal to 1 and y prime of 0 is, say, equal to 2. You need two things because you have two constants you need to solve for, so you need two equations, two systems of equations. So, but I will usually tend to keep the I just for emphasis that the I is actually there. That's up to you. But with this general solution in mind, I'm thinking just an example will be needed, and then that will be that for second order differential equations. So maybe y double prime plus 2y prime plus 4y equals 0. The characteristic equation is r squared plus 2r plus 4 equals 0. So r is equal to negative 2 plus or minus the square root of 4 minus 16, the b squared minus the 4ac, all over 2. So that's negative 2 plus or minus. Now we have the square root of negative, I'll just write it like this, negative 12 for now, over 2. And negative 12 is what? 2 square root 3, so negative 2 plus or minus 2i square root 3 over 2. Or in other words, negative 1 plus or minus I square root 3 is the r value. And, oh, one other thing I wanted to point out, I almost forgot, but I'm going to mention it here. I picked originally the positive version, in other words, a plus bi. If we were to pick a minus bi here for the general solution, all that would happen is, so we would just have a negative bt, and cosine of negative bt here is just cosine of bt, and then sine of negative bt is just the negative sine of bt. But if we just pick c sub 2 to be negative and we're subtracting a negative, then it becomes a positive. So whether you pick the positive or the negative, it does not matter in the overall solution. Okay, so then the general solution to this differential equation is y equals c sub 1 e to the, now this is the negative 1, here is the a, and the square root 3 is the b. So this is c sub 1 e to the negative t times the cosine of root 3t. There's no radical under the t, just under the 3. Plus c sub 2 I e to the negative t times the sine of the square root of 3 times t. And that is the general solution to that differential equation. And sometimes these things can get messy, you know. It was nice there that the factors of 2 all canceled, but I mean, don't get intimidated by the messiness of it all. I mean, you really are just sticking your value of r as a coefficient in front of the t on the exponent of e, and that really wraps it up for